everyone. My name is Iman Valizadeh, and I'm working as research assistant at Cyber Physical Simulation Group and Additive Manufacturing Center under supervision of Oliver Weeger at Technical University of Darmstadt. Today, I'm going to present our recent research, which is the parametric Visco-hyperelastic constitutive modeling of functionally graded polymers, which are manufactured by Grayscale master stereolithography method. Let me start by introducing some of the application of this printing method. The idea is that mainly we can change the process parameters, and by changing the process parameters, we change the monomer conversion, the degree of monomer conversion in every point of the material, and then we can print the graded structures. We see, for example, this lattice structure, which is printed with different light intensities, which can be regulated through the grayscale values of the mask, and then it has different mechanical properties in its layers. And under the different loading directions, under the compression, it behaves differently. Because of the tunable mechanical glass temperature, this material can be used as shape memory polymers. We see, for example, this helical pattern, which is printed with different grayscale values, and after the programming and heating, it recovers its initial shape. The other application is, for example, in soft robotics, we see the arm of this robot, which is printed with different grayscale values. I want to mention that in our previous study, we developed a hyperelastic constitutive model in terms of the grayscale values, and we compared the experimental and numerical strain curves for different geometries, which are printed in different directions, which are grayscaled in different direction, and then we got a very good agreement between the numerical and experimental results. Now let's have a look at the printer structure and the printing method. The solid part, the 3D solid parts are designed in the CAD software and sent to the printer through a slicer software. This type of printer consists mainly of a UV light source, and the UV light is transmitted from this source onto the LCD chip, and the LCD chip reflects the filter light onto the optic lens, and this optic lens regulates the transmitted area and focus on the tank of the liquid resin. As the UV light penetrates the resin from the bottom, the photopolymerization takes place, and we can print the 3D solids. The masks which are uploaded on the LCD chip, they consist of black and white pixels. This mask represents each layer of the 3D solid which we are going to print. And they consist of black and white pixels, and the black pixels block the light, and the light can be fully transmitted through the white pixels. And this leads to full photopolymerization in the resin. The idea is if we change the color of the white pixels to gray, the light can be transmitted partially through these pixels, which leads to partial photopolymerization in the resin, and therefore we can change the cross-linking density, and then we change the mechanical properties at every point of the layer which is under the printing. And therefore we can print the graded structures. So one of the important process parameters which can be regulated through the grayscale values of the mask is the light intensity, and then the other one is the time of the UV exposure, which is the exposure time. By increasing the exposure time, the time of the exposure increase, and this leads to more crosslink density and increasing the degree of monomer conversion, and we get a stiffer material because we have more cross-linking network density in the material. You see here the schematical illustration of the chemical component on the structure of the polymer under the printing, which consists of the monomers which are connected from two sides to the crosslink network, and this represents the equilibrium part of the material. And we have the monomers which are free or which are connected from one side to each other, and they represent the non-equilibrium or viscoelastic behavior of the material. And based on that, we are going to develop a Visco-hyperelastic constitutive model, which we see in the next slides. As I mentioned, we have two process parameters. The exposure time and the light intensity. Increasing them increase the radiant energy, and increasing the radiant energy increase the degree of monomer conversion, which leads to increasing the cross-linking network, and finally, we increase the mechanical properties. The radiant exposure is the irradiance times the exposure time, and we can regulate the light intensity through the grayscale, as I mentioned, and we measured the light intensity for different grayscale values to determine the correlation of these two parameters, and we got a quadratic relationship between the grayscale and the light intensity. And based on that, we introduce a new parameter, which is the grayscale exposure, and is the grayscale squared the exposure time. This grayscale exposure, the new parameter, is a single unified parameters and can be influenced through the process parameters and represents the correlation of the both process parameters. In the next step, we want to get the material behavior and material response under the mechanical loading. We see here the stress strain curves of the uniaxial tension test for different values of the grayscale and exposure time and for different strain rates. And to get the rate dependence behavior of the material. We see here the experiments and the fitted stress strain curves to the experiments, which we see in the next slide. And through this fitting process, we determine the constitutive constants. But before going to constitutive model, let's have a look at the experiments in more details. We have here the stress strain curves from the experiments for constant grayscale values and different exposure time. And by increasing the exposure time, we see that the stiffness of the material increase. Here we see the stress strain curves from the experiments for constant exposure time and different grayscale values. Interestingly, we see here that the stress strain curves are less sensitive to the change of the grayscale for larger values of the exposure time. For smaller values of the exposure time, the change, the stress strain curves are more sensitive to change of the grayscale values. Now let's move on to the constitutive modeling. We have a nearly incompressible visco-hyperelastic material, and then we use the additive decomposition of the energy function into the volumetric, isochoric, and inelastic part. We use a Munir-Rivlin material model as an energy function, and we calculate and we get the stress by which is in case the second Piola-Kirchhoff stress, and is a derivative of the energy function with respect to the Wright-Cauchy-Green strain tensor. And we use a linear evaluation equation for the inelastic part of the stress. I don't go into the detail of the formulation, but I want to show here that the final form of the stress are formulated in terms of the grayscale exposure. That means for different values of the grayscale exposure, we get different constitutive constants and different stress strain curves. So we fit this material model, this constitutive model to the experiments, and we determine the constitutive constants for equilibrium part. We see here that by increasing the process parameters, the absolute value of the constitutive constants increase. We have here the shear modulus, which is plotted for different values of the process parameters. And we see that by increasing the process parameters, the grayscale exposure increase and the shear modulus increase. But after some points, it converges to some values here. That means from this point, by increasing the process parameters, the shear modulus cannot be increased and the material cannot get stiffer. And that is the final stiffness that we can have in the material. The reason is that from this point, we don't have enough free monomers to join the network and increase the cross-linking density. In this plot, we see, in this two-dimensional plot, we see the shear modulus for different values of the process parameters. On this line, we have always a constant shear modulus for different couples of the process parameters. And therefore, we see the correlation of the process parameters and the mechanical properties and their influence, that we can have identical shear modulus for different values of these two process parameters. So the next step is that we want to determine the constitutive constants for any arbitrary grayscale exposure. Regarding the behavior of the material, and we propose a tangent hyperbolic function. We see these dark triangles from the experimental fitting, from the experiments, and the fitting constitutive model to the experiments. And then we fit this tangent hyperbolic function to the experiments to determine the constants of this function. And we see that the maximum values in the maximum value in this function coincide with the maximum value of the curves. And we have some coefficients to establish the our tangent hyperbolic function. So now we establish our constitutive model, and we want to validate the hypothesis and the constitutive model that we saw in the previous slide. The idea was here that for different couples of the process parameters which have identical grayscale exposure, we have similar behavior in mechanical properties. We plot here the stress strain curves for different strain rates and different couples of the process parameters. Two of them are from the experiments, and one of them is new values by using the tangent hyperbolic function. And we compare here the experiments for different strain rates. First, we see that the stress strain curves from the experiments, they have a similar behavior for similar grayscale exposures. And we see the red lines, which is the numerical stress strain curves, and can approximate the experimental curves with a good agreement. In the next slide, we compare the numerical and experimental stress strain curves for different strain rates and for totally new couples of the process parameters. Use the tangent hyperbolic function to determine the constitutive constants, and we see that there is a good agreement between the numerical and experimental stress strain curves for different values of the grayscale exposure. In the final validation, we want to validate the inelastic behavior of the material. We compare here the stress strain curves from the experiment and from the constitutive model for new strain rates, and we see that the constitutive model can approximate the experimental stress strain curves with a good agreement. Now I want to summarize the main points of this research. We investigated the influence of the process parameters on the mechanical properties, and based on that, we introduced a new single unified parameter which represents the correlation of process parameters. We developed a parametric Visco-hyperelastic constitutive model in terms of grayscale exposure for grayscale 3D printed graded polymers. And then we proposed a hyperbolic tangent function which can be used to determine the constitutive constants for any arbitrary grayscale exposure. And we got a good agreement between the numerical and experimental results. And in future, this constitutive model can be implemented in numerical frameworks to design, simulate, and optimize the graded 3D printed polymer structures. Thank you very much.